systems of ordinary differential equations. We're going to write, I'm going to say the following. We're going to consider a vector. We're going to use this notation. Physics, this is very common in physics to use that arrow on top of a symbol. That's going to denote a vector. We're going to say, look, consider this vector which has entries x1 of t, x2 of t, all the way through xn of t. Consider this vector, and also let's consider a matrix. Let P be a matrix that has entries P sub 1, 1, P sub 1, 2. These are all the entries on the first row, P sub 1, n. And they go all the way down to row n. So this would be n1, P sub n1, P sub n2, all the way through this corner, which would be P sub nn. So this is to say that P, as specified here, is a matrix. In other words, that is, P is an n by n matrix. It could be an n by n matrix with entries that are complex numbers, you know. So now we're going to consider writing the product P times X. Okay, so if we write P times this vector X, this would be this matrix, times, I'm going to omit the dependence on T. This vector is going to have entries X1, X2, all the way through X sub n. And these are the entries of the matrix, P11, all the way through P1n, and here you have P sub n, n. So that product of that, this is a matrix vector product. We have a square matrix multiplying a column vector, so this product, there are two ways of doing this matrix product, right? I think here I've spoken mostly about one way in which you would collect the columns of this matrix, okay? So you write one column here, another column over there, another column over there, right? You could write this as a sum. And what you would be saying is, look, here you would have P, here you would have X1, X2, X3, all the way through Xn. Each of these entries of these vectors are the coefficients in a linear combination of the columns of this matrix. So that means that the first column has P11, P21, all the way through Pn1. Second column would have P12, P22, all the way through Pn2. Next column, P13, P23, all the way through P sub n3. Last column is P1n, all the way through P sub nn. Almost running out of space there, right? So if you could write this in such way, there's another way in which you look at a row and express this as a so-called inner product. But if we do this, we are gonna end up with a first column here. Okay, a first column that has all those numbers in the entries of that column, P11, P21, but we would have P11, X1, P21, X1, right, and this continues here, and then Pn1, X1. So those would be the entries on the first column. I'm gonna go ahead and write this last column here. The last column would have P1n, Xn, all the way down to Pnn xn. Which means that that product of that matrix P times the vector x is going to be a vector itself. And every entry of the vector, let's write one more line. Right? So this is a vector. The first entry would be P11 x1. Second entry is P12 x2, all the way through P1n xn. The last entry would be Pn1 x1, all the way through Pnn xn. So this product of the matrix P multiplied by this vector x1, x2, x3, xn is a vector such that every entry of the vector is a summation of x1, x2, x3, xn. This vector x is actually called the vector of state variables. Okay, so in this notation, this vector is called state variable vector. That's what we call this x with entries x1, x2. So each of those entries, x1 of t is a state variable, x2 of t is a state variable, xn of t is a state variable. Okay, and so this product of this matrix P multiplied by the vector of state variable is a vector that has these entries, and each of these entries is a summation of the state variables. You may argue, well, that looks like a linear combination. Yeah, it is. It is a linear combination. That's where each of these entries comes from. Okay, so this will be the notation for the so-called systems, particular linear systems of ordinary differential equations. So we're going to write systems of differential equations in the following form. We're going to consider the derivative with respect to t of the vector of state variables. Well, maybe I can do this in two. Let me do this in two steps. So we're going to write derivative of x1 equal the first row of this vector p11 x1 all the way through p1n xn. Then derivative of x2, that would be the second entry on this vector, which is p21 x1 all the way to p2n xn. And then we consider derivative of x3 and so on. And so the last derivative would be indicated. Derivative of xn is given by the last entry of that vector, which is pn1 x1 all the way through pnn xn. So this denotes a system of differential equations. There are n differential equations. There is one derivative for each state variable. So there is the first equation here is the derivative of state variable x1. Second one is the derivative of x2. There is dot 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 means there is the derivative of x3 in between, and this goes all the way to up to the end, the derivative of the state variable xn. Each of those derivatives is a summation of the state variables such that these numbers p sub ij, each of those coefficients is an entry on that matrix with n rows and n columns that I'm calling here the matrix P. So this is the long way of denoting a linear system of ODEs. The short way, we can also write the derivative with respect to d of that vector x, the vector of state variables, to be equal to the matrix P multiplying the vector of state variables x. So the derivative of x with respect to t equals P times x. Right? So this here belongs to Cn. This is a vector in Cn where x is also a vector in Cn, and P is m sub nn. That's a way of saying that a matrix has n rows and n columns, the square matrix. So in this context, there is one way of finding the general solution of such type of. So far, we have discussed first order, second order, higher order linear differential equations, but in each of those cases, we had only one equation. Even when the equation involved higher order derivatives, we only had one. Now that we have a system, it means that simultaneously, we have more than one equation. So we would like to find not just one state variable, but the set of state variables that here is collected as a list or a vector. Would like to find x1, x2, x3, such that all those equations are satisfied by those state variables at the same time. If you find one, and what we're going after is finding x1, x2, x3 all the way through xn, such that each of those x sub k or x sub j is a function of time. So it really is x1 of t, x2 of t, x3 of t, x5 of, all the way through x sub n of t. So this is, of course, if the derivative here is denoted as with respect to t. I could also write that as a system d of y with respect to x, and then it would be every state variable would be a function of x, right? So each state variable, by given the notation by what I'm writing there, is each state variable is a function that depends on the variable t.